Well, here we are. Complex analysis. Kinda strange nearing the end of SoME.
And this time, my indexing isn't going to be as bad.
You're saying as, it makes it sound like you're not entirely sure.
Yeah.
Anyways, for those who don't know, this is I, the imaginary unit, and it's equal, in fact defined, to the square root of -1.
The numbers that can be written as a plus bi, where a and b are real numbers, are called the complex numbers. Now it's finally time to see the problem. That's right, today we are looking at analytic continuation. Hit it!
Okay, enough about that.
First, what is an analytic function? It's a function which is locally given by a convergent power series. That is, it can be approximated like this.
Another way of thinking about it is that the Taylor series of the function centered at any point x0 in its domain converges to f of x. For example, polynomials, exponential functions, and the like.
But here's the problem. You can't really take the logarithm of a negative number, let alone an imaginary number. And what does it mean to raise e to the power of I?
Well, all of these have a Taylor series, so we can just plug the numbers in and we're good to go, right? Right?
Yeah, this isn't gonna work. The problem is that the log function diverges at 0, so for all we know, the right hand of the function could look like this, or even this. Here's where complex numbers come into play. What if we leave the realm of the real numbers and see what functions looks like for, say, z equals I plus 1? Then we can go around and finally figure out log of -1.
Okay, so for z equals 1, the radius of convergence, that is, the interval in which the function converges, is just 1.
Of course, there may be other points of divergence in the complex domain, but the radius of convergence can be found out by the Cauchy-Adamnar theorem.
Since the point z equals 1 plus I lies on the circumference of this radius, we can't say for a certain whether it converges, so we better make that 1 plus a half I.
Or a half plus a half I.
Sure, let's move it to the critical line, why not?
Oh? You want to know what the critical line is? I'm sorry, but that is a story for another day.
Also, it's preferable that the absolute value of a is greater than the original radius of conversion, so we're absolutely sure that our new domain is larger than the old one.
But this will work for any value of a. That's why we're just going to call it a instead of a half plus a half I. That and it makes it easy to follow. Anyways, our next step is to focus on recentering the power series on a. We know that the function is defined for this circular region and its boundary, call it D.
Oh yeah, we forgot to name our original region. Let's just call it U. So how are we supposed to recenter it?
Using what's known as Cauchy's integral formula. For every a in the interior of D, f of a is equal to this integral along the boundary. I won't get into the details, but the reason for this is due to the Cauchy integral theorem.
This Cauchy guy has named a lot of things.
Not as many as Polygon. There are some details I'm kind of glossing over here, but it should be fine. The point is that this is equal to this. Now let's calculate the coefficient of ak. This is equal to the case derivative of f at a over k factorial, which is equal to this. Now let's assume we don't know f is equal to the log of z.
This is to show the general process, right?
I suppose. Let's replace f with its Taylor series. In this case, we can place the integral in the sum and take -1 to the n plus 1 over n out. We know that dabba d is a circle, so we can parameterize the form of polar coordinates centered on a. Since zeta equals a plus r e to the I zeta, d zeta equals r I e to the I zeta d zeta.
But then we can cancel out an r e to the I zeta from the numerator and the denominator. And then I guess we can cancel out these i's, and I don't see where to go next.
I suppose we want to cancel out these r to e to I zetas. I think we can use the binomial expansion on a minus 1 plus r e to the I zeta to get this, which means we can take all this out. And now we have this. And now we're stuck again. I actually don't know how to solve this.
Wait, if you don't know how to solve this, then what are we going to do? Wait, what's happening?
I think it's your mathematical objects thing. What? Huh? I see. That makes sense.
It's all clear now. Take the integral from 0 to 2 pi e to the I n zeta. Whenever n is an integer, e to the I n zeta makes n full loops around the unit circle, touching every point in this circle equally. Since you can pair each point with the point offset and every pair points add to 0, then the total integral equals 0. The exception is when n equals 0. Then e to the I in zeta just equals 1 for all values of zeta, so the integral ends up equaling 2 pi.
So we can get rid of the case where m equals anything other than k. Also now we don't need to start this summation at 0, we can just start it at k. In short, we get this. Now we can make one more substitution, u equals n minus k, just so the summation starts at 0. We can split negative 1 to the u plus k plus I and bring the negative 1 to the k plus I for n outside, and combining the negative 1 to the u with the other thing. Now, does this look familiar?
Not really.
Well, here's a little nifty formula. You can figure it out yourself by derivating the geometric series. Substituting x for 1 minus a, we get that this part is just equal to 1 over a to the k plus 1.
So that's the coefficient for the extension for the log function. So this must be our completed formula. Now that we have a new center, we can find a new radius of convergence and extend the domain of the function by that new radius. If we keep doing this for different points, we'll eventually have the entire complex plane covered, and we can finally find out log of negative 1.
Funny thing about that, apparently you can't actually get negative real numbers into the domain. However, those values can be obtained as limits of values at nearby complex numbers with positive imaginary parts.
I see. Still a bit of a bummer that we did all that work for nothing.
Wait a minute. Will our question of the complex logarithm be next week's question?